All right, so today we're looking at average value of a function f of x on an interval ab. So imagine we have this function here, and we were looking for what's the average y value, right? And it's kind of easy to imagine that if this curve here represented some kind of like a hard barrier, and underneath it was all water, and this like pushed the water around, and there was no space in between the water and the actual curve itself, and it went all the way down to the x-axis. Well, if you were to take this hard barrier off, the water would slosh around until it found some kind of like a level that we could call that the average value of f of x. All right, and so we're trying to figure out what that average value might be. So if you remember, an average of a number of data points would be to add them together, all of them together, and then divide by how many there are. So in this case, there are n values. Okay, so now this is going to be kind of hard to do, but we can think of almost like breaking it up like a Riemann sum and saying, okay, let's, we can't possibly calculate all the infinite number of values in here from a to b, so let's only calculate n values going from a to b. And so let's divide up the length from a to b into n subdivisions. And so that would be, if we take b minus a and divide by n, we get these little kind of changes in x that are little tiny distances here, right? So you're going to have all these little subdivisions, and they're going to have these equal lengths, distances of delta x. Of course, we can rearrange this in terms of n and write this as n equals b minus a over that little change in x. Okay, so that's just rearranging it and solving for n. Now, inside each of these little subdivisions, we can pick x values, for each one of these. So you're going to have your x1 is going to be inside the first subdivision, and same thing with your x2 and x3 and so on, and we want to average them together, right? So that would be adding up all of these x1s, the y values from x1, x2, x3, and so on, all up until the last x value. And of course, this is divided by how many there are, n. And so this is your average value, or at least it's an approximate average value. Okay, all right, so now what I'm going to do is I'm going to substitute this in for n. This is going to give me f of x1 plus f of x2 and so on, all the way up to f of x sub n. And now this is going to be over b minus a over delta x, right? Now, I don't like having complex fractions here where you have a denominator like a delta x, so I'm going to flip and multiply by its reciprocal and kind of rearrange it a little bit, right? So this equals 1 over b minus a times, now this delta x is going to flip up and multiply times that numerator. So we get f of x sub 1 plus f of x sub 2 plus f of x sub 3 all the way up to x sub n, and this will be times delta x. But this here is a sum. So I'm going to write it with summation notation because we're adding together all of these y values, and I'm going to say I equals 1 to n, and multiplying it by this delta x. Well, that is a Riemann sum, which is an approximation for an integral. And in fact, if we take the limit as n goes to infinity, as the widths of our subdivision get more and more and more, and subdivisions get smaller and smaller and smaller, we're getting those widths end up going to go to infinity here. So the widths go towards 0, and we're multiplying it by more and more and more of these y values. Taking this limit gets us that integral. And so we get the average value being 1 over b minus a times the integral from a to b f of x dx. And that's how we find an average value. All right, it's the same thing as an integral, but then times it by 1 over b minus a. So let me take an example here, right? Find the average value of this function here on the interval going from -1 to 5.5, right? So this is our function, this is our f of x here. We've got this like sinusoid or cosine wave graph that's going down, it's decreasing over this interval, right? And we're trying to find the average y value on this. And we're starting here at -1 and ending over here at 2.5. So we can do this by taking the integral from -1 to 5/2 of x squared minus 5x plus 6 cosine of pi times x dx. Now this is an integral that adds up all of these infinite y values, and we just have to average it out by multiplying by 1 over 5/2 minus -1. Calculate the integral, multiply by that fraction, and we will get a value like -1.62. And if I graph that value on here, -1.62, we can see that between all of these y values up here and all of these y values down here, that about -1.62 looks like it's about in the range here. Now, some of the questions you're going to come across are going to actually ask you to do one more thing. And it's almost like the mean value theorem for integrals, in that there has to be some value c that's inside this integral, that's in between -1 and 5/2. I should make that an open interval. So there's some value in there such that f of c is going to be equal to that -1.62. And if I graph it on Desmos, we can see that there are actually 3 values that have that average value as a y value. Okay? Some of the questions on WebWork are going to actually ask you to find this c. If you can't solve for it, go ahead and graph it. Graph it in Desmos, look for the intersection like I did down here, and we can figure out where the value is such that 1 over b minus a integral from a to b f of x dx, which is the average value of the function on there, is going to be equal to some c value, where c is in the open interval AB. Okay, and that's our mean value for integration, right? It's kind of like saying, If our average speed going from here to the New York City was 60 miles an hour, then you got to hit 60 somewhere, at least a couple times, okay? Good. So that is average value of a function. There's a couple problems on that in the homework assignment. Please try them, and stop by with my office hours if you have any questions. Thanks.